Hi, good morning, everyone, fellow data scientists and attendees. My name is Connie, and I'm on the data and analytics platform team at Bloomberg. And my team owns the query platform for all financial data. And so essentially what that is a single point of entry for all Bloomberg applications to be able to access all the data that Bloomberg has available. And so today I'll be sharing with you some of the challenges in processing raw financial data and how we can use data science and machine learning to solve them. But before I get into the main presentation, let me give you a brief intro on Bloomberg. We pride ourselves as the central nervous system of global finance, and that's because we're able to accurately deliver business and financial information, news, and insights to customers around the world. Bloomberg's main product is the Bloomberg Professional Service, also known as the terminal in the financial world, and it provides access to vast amounts of data in various formats, such as billions of pricing ticks a day to millions of news stories and company financial reports. And that's the picture of a terminal if you haven't seen one before. All right, so I'll first start off with like the typical data science workflow, and then I'll get into the need for data extraction, specifically from natural documents. I'll explain what they are in a second. And then the next part of the presentation will be on data cleaning, specifically on text data. And finally, I'll wrap up with some concluding remarks and takeaways. All right, so every data scientist knows that data processing and data cleaning are essential to any data science project, because raw data can be in various formats, right? You have strings, numbers, documents, charts, and the two steps they need to take to bring from raw data before you can do any modeling analytics are two main steps. One is data extraction, which is the conversion of raw data to machine-readable format. And the second one is data cleaning, which is some quality assurance that your data is correct. And so the focus of this talk will be twofold. One is data extraction specifically from natural documents that contain tables and charts. And the second part will be on data cleaning. After you've extracted data and you find that most of your data is text, how can you make sure that it's clean? So let me jump into the, well, I think it's jumping too far. Okay, so let me get into the data extraction piece first. All right, so natural document formats are used to present data in a way for it to be easy for a person to interpret. And examples are PDFs, images, bars, and line charts as shown here. But the challenge arises in how do we extract the visual and spatial format that's in this format. How do we extract the raw data that was presented in this chart? Because you may need this data for further processing and analytics. And as I mentioned before, Bloomberg has a lot of financial documents, and some of them have scatterplots, but they don't have any associated tables with them. So we don't know what data points were used to generate them. So is it possible to derive this data, right? So this is the data extraction part. So this general strategy that you may come up for scatterplots can be, first, we may want to do some object detection on your plot, right? Find the most important objects in your plot, which are essentially the points, which are have bounded boxed in blue here shown. We have tick values, which are in red, and tick marks in green. And after you've identified these objects, maybe you want to do some OCR, optical character recognition, on these tick values. And then finally, find the conversion factors between pixel coordinates and chart coordinates using regression. Let me go a little bit more detail on the, go up a little bit, on the first part, the object detection. So the naive approach may be to come up with like a huge number of regions in your image, and then try to classify whether it contains your object or not. But this is very computationally intensive. So some of the state-of-the-art solutions, they're actually, you can get them out of the box, such as RCNN, the first two, RCNN and fast RCNN. What they do is they have some region proposal algorithms to kind of hypothesize where the objects are located. So the first two I've noted at the top. The second one is faster RCNN, which is actually faster than its predecessors. And that's because instead of using a selective search algorithm, it uses another network to try to predict the regions. So the picture on the right is the architecture of the faster RCNN. I'll just walk you through quickly what happens. So essentially, you take an image, you pass that through a convolutional neural network, and that network generates feature maps. And then from this feature map, instead of using some algorithm to selectively search some regions, it uses another network to try to predict where they're located. So these proposals are then passed through another layer, which are then classified, whether it contains this or not. RCNN, the top three of RCNN flavors are available in Caffe. TensorFlow has its own implementation in TensorBox and the object detection API. So in order to train object detection models, it requires a lot of data. And instead of annotating plots, what you might want to do is to synthetically generate them. And what we ended up doing was using Python's library, matplotlib, to generate random images. And by generating them randomly, you know exactly where the objects are located. So once you keep track of them, then it's easy for evaluation later on. There's no need for annotations. And so here are some examples of the randomly generated images. Yeah, I think this keeps popping. Okay. So we took all this general approach, put it all together in an end-to-end system. We called it Scatteract. And essentially, what it does is it takes a scatter plot on the left, and it treats it as an image. And the output is a table of x and y coordinates of the points. We have two tables here. The left is the predicted values, and the right is the actual. You can see that it's pretty, I think it jumps a lot. Okay, you can see that it's pretty close. So to evaluate the performance of Scatteract, we define true positives as predicted points that are within 2% of the real points. And we define a success on a chart if the F1 score is at least 80%. On the randomly generated plots, we get an overall precision of 88% and overall average recall of 87. And here on the right is the distribution of F1 scores for all the randomly generated plots. We also wanted to see how Scatteract performs on real charts. So in visually inspecting 50 charts from the web, we get about a 78% success rate. And here are examples of two charts from the web. You can see that even where the points are clustered together, we're able to detect each point accurately. I think they're missing a couple on the right, but there are some limitations, of course, when you do have a lot of clustered data points. And this code, Scatteract, is open source together with the data sets that were used. So feel free to check it out, play with it, and pull requests are welcome. We also have further details published in the paper in ECML. So please read that if you're interested. Some future direction notes. We are moving on to different types of charts because, as you know, financial documents contain pie charts, bar graphs. Similar techniques can be used using computer vision. Secondly, some charts contain legends, so can we characterize the points using that information? And lastly, what I described so far is data extraction, right? But that's assuming that you have that image of a plot readily available. But in reality, you usually have a document with text, tables, charts. So how can we localize the chart and then classify it, whether it's a bar chart, a scatter plot, or a pie chart? So developing the rest of the pipeline is also necessary to do this full extraction. Okay, so now I'll jump into the data cleaning part of the talk. So data cleaning is basically comprised of two parts. One is anomaly detection and then correcting for those anomalies. There are some classic anomaly detection techniques that are proposed in literature, we have our standard density-based family. This assumes that the anomalies fall in these low-density regions. And some examples are k-nearest neighbors, isolation forest. And we also have another type of technique called the one-class SVM, where you kind of train your model on normal data, and then you classify your test data, whether it's anomalous or not, depending on how far away it is from the normal data. But for text, there's no well-defined technique for detecting anomalies. And one of the main reasons why that is so is that anomalies in text come in many different forms. We have misspellings, encoding errors, punctuation, grammatical, and contextual errors. And there's no like well-defined format, and any rules-based system just isn't scalable. So here in this table are some examples of anomalies that were detected by an unsupervised deep learning approach that I'll describe on the next slide. So just to walk you through this, this approach, let me begin with an example. Let's take the phrase real estate. And on the bottom left, we have an LSTM where it reads the input sequence byte by byte, and it tries to predict the probability distribution of the following byte. And here in this trapezoid in green, I have an auto-encoder layer. And what that does is it tries to learn the minimum amount of information it needs to make that prediction. And so this is encoded in a context vector. This is essentially your feature selection process. And now this context vector is then used to train a one-class SVM. And so in analysis, let me just back up a little bit. So the one-class SVM is to use for you to form a boundary between what is good and what's bad data. So in analysis, we load this model, and we read the input string byte by byte. And we try to predict whether it falls in or out of the boundary. So when we reach the semicolon here, we see that the context vector actually fell out of the boundary. And so we flag this semicolon as an anomalous byte. So how do we evaluate this kind of approach? One way is to use crowdsourcing, having these detected anomalies ask trained humans whether there is an error involving or around this highlighted word. This is the detected anomaly, and they answer yes or no. So using this information, we can determine the precision of your model. And so this particular one, we ran it on a couple data sets. It performs the best on job titles with a precision of 57%. So how can we improve this further? One way is to introduce some kind of bidirectional LSTM. So what I described earlier is that it encodes context from sequences that occurred before the current character, right? But oftentimes the context afterwards can help improve predictions. And secondly, the current context vector is one fixed size, and that has limitations when decoding longer sequences. So using some sort of attention mechanism to focus on certain parts of the input can help as well. Whoa. All right, so in conclusion, we sort of all know that proper data extraction and data cleaning are common challenges when working with raw data. And here in this talk, I went through some ways in which we can extract data from natural document formats and cleaning textual data. And the solutions include Scatteract for Scatterplots, and other similar techniques can be used for other types of charts. And then for detection of anomalies in text, since there is no well-defined technique, some sort of unsupervised deep learning approach may be suitable for your case. Bloomberg is hiring. You can talk to me offline on opportunities and all the cool projects that we're working on. And yeah, I'll take questions now.
All right. Our first question is from Josh. Are these methods to interpret printed charts meant to read external published graphs to essentially digitize financial documents?
I didn't get the first half of the question. Can you?
Sure. Are these methods to interpret printed charts meant to read external published graphs to essentially digitize financial documents?
Yes, that could be a use case. Yes. I think what I described here is if you wanted to know the information that is embedded in a chart, and then let's say you wanted to do some more analytics on the data points. But yes, digitization of charts is also a valid use case.
From Arya, how does the algorithm perform on logarithmic or nonlinear scales versus linear ones shown in the presentation?
Yeah, that's a good question. So we built this algorithm on linear scales graphs. We haven't, I guess, accommodated for other types of scales, and I think with another, I didn't go through the regression technique that was used, but in order to address log linear or logarithmic scales, I think we would need to adjust the regression technique that was used to do the conversion between the two pixel to the chart coordinates.
Carlos asks, is this data capture method used to feed Bloomberg products? How do you handle the data accuracy errors that the Scatterplot capture introduces?
So right now, the extraction piece is not in production. It's more like a research project. Yeah. So.
Gray asks, is plus or minus 2% accuracy a universal acceptance threshold for Scatteract, or are there types of data where you are more or less lenient?
Well, we decided to use the plus or minus 2% because also, as you can see on some of the charts, most of them are very clustered. So if you're plus or minus 2% away from the actual value, it is like good enough for us. You can, I guess, adjust that to your needs. I think the most critical point is being able to object detect on points that are, what we found is that the points that are clustered well together, being able to isolate each and every one of them is a challenge. So if you do have points that are maybe like very far apart, then you should probably decrease that threshold.
Carlos asks, I am curious to know what type of kernel method you used in the SVM.
Oh, it's a standard like RBF. You can also try other kernel methods. Yeah.
Tim asks, how do these algorithms perform on charts that have embedded labels and over or dual axis charts?
Embedded labels?
How do these algorithms perform on charts that have embedded labels and over/or dual axis charts?
I'm not sure what the second part means, but embedded labels, I guess I need to talk to you to get clarification on what you're asking.
Kevin asks, are the financial charts made in-house, or is Scatteract mainly used for other companies' graphs? Could you do end-to-end deep learning for a future iteration of Scatteract?
Okay, I got the second half of the question. So the second question was the end-to-end part, and that's a very good question. It is possible, and I think there are papers out there following Scatteract's publication on that. I didn't get the first question.
Are the financial charts made in-house?
So the training data was generated synthetically, as I explained. That was so that we didn't have to manually annotate the data. Yeah.
Nolan asks, how accurate does this tool need to be before it will be deployed?
That is a good question. I don't have the answer for that.
Michael asks, as a follow-up to the plus or minus 2% accuracy question, did you look at how well humans interpret charts? Are humans better or worse than 2% error on highly clustered plots?
Are humans better than plus or minus 2? So let me just answer that by saying that we actually started this project by seeing that some people, when looking at a document that has charts, they would pull out like a ruler to try to measure, right, like how where the points are and the values of them. And so from that, I feel like being able to not able to see it visually without some kind of tool is not as precise as an algorithm that can do it using these kind of techniques.
I see a few more people typing. All right, Josh asks, what population do you use to validate the accuracy of the models? Are they Bloomberg SMEs or public mechanical Turks?
Oh, okay. No, they are just mechanical Turks. Yeah. I mean, at least for the data, the evaluation that was showing for the textual data, they don't require SMEs, but it may vary depending on your data set.
All right, that looks like everything. If you guys have any more questions, feel free to follow up with Connie on Slack. She'll be around to answer them. Thanks so much.